Hello, welcome to lecture 24 of the course. This is lecture number 3 of module 3. In this lecture, we'll continue our discussion on basic physics qualitatively. Then we'll start discussing the so-called fluctuation dissipation theorem, which will be very important for our later classes. So let us begin. In the last class, we discussed about the quality factor Q of a Fabry-Pérot cavity, and we saw that quality factor and finesse of the cavity are related very closely. In fact, they are actually the same, only quality factor is expressed in a different frequency unit than that of the finesse. And quality factor and finesse both refers to the fact that for example, say Q is equal to 10 to the power say 6. That means that the photon will oscillate inside the cavity around 1 million times or 10 to the power 6 number of times. Then we started discussing cavity optomechanical system, and firstly, based on logic, we tried to guess the Hamiltonian of the cavity optomechanical system. The total Hamiltonian of the cavity mechanical system will consist of primarily 5 parts. One is due to the optical photon inside the cavity, and optical photon, as we know, that it is basically a harmonic oscillator. Then the mechanical oscillator, which is basically due to the movable mirror, that is vibrating in the range of gigahertz or kilohertz. Okay, so they are basically quanta of vibration, they are called phonons. So that is also again another harmonic oscillator. And then there is interaction between optical photon and phonon, and that is because of the fact that when the photon hits the movable mirror, it displaces the mirror by an amount x, and thereby both photon and phonon get coupled by the parameter x. And this laser cavity optomechanical system is driven by a laser. Apart from that term, there are other terms due to the dissipation, because both the photon as well as the phonon may decay. And then because we know that the cavity photon is basically a harmonic oscillator, and now this resonance frequency of the oscillator is dependent on the displacement of the movable mirror. So based on this, if the displacement of the mirror is very small, then we got the two terms. One is due to the cavity photon that is circulating inside the cavity, and another one is the optomechanical interaction term. And we also saw how the radiation pressure force can be very easily worked out, and this is related to the number of photon inside the cavity, as well as the bare optical cavity resonance frequency. And the optomechanical interaction Hamiltonian term can be expressed in a very convenient form like this. Okay, so that's what we did in the last class, and we were able to write down the full Hamiltonian of the cavity optomechanical system. However, we are not discussing how to write the expression for the dissipation term and the laser drive time, which we will do it in a later class. After that, we started discussing the basic physics of a cavity optomechanical system in a qualitative way, assuming that the photon that is getting incident on this movable mirror reacts instantaneously to the position of the mechanical mirror. This we can assume provided this mechanical mirror moves very, very slowly. So this is basically the static case, and under this static case we discussing the so-called optical spring effect. What happened is that because this mechanical oscillator is basically a spring, it's a oscillator, it's a harmonic oscillator, so it has a intrinsic spring constant, but due to the radiation pressure force, the spring constant of the mechanical oscillator can be modified, and that is what this that comes due to the radiation pressure force. This is also we discussed in the last class. And we have taken another perspective where this whole thing could be understood using the radiation potential, because the radiation potential is and force is related, because force is equal to the negative of the derivative of the potential with respect to the position, as you can see from here, and this will result in a staircase kind of a potential, and this potential has to be added to the harmonic oscillator potential, which is basically the intrinsic potential of the mechanical oscillator. Then the resultant potential will look like this blue curve here, and based on this we saw that and we discussed that we obtain the what is the phenomena called multi-stability, because we can have a number of local minimum. Also we saw that the restoring force and the radiation pressure force in a typical cavity optomechanical system, they may balances at some points. For example, here in this figure, at point A, B and C, the radiation pressure force is exactly equal to the restoring force. However, only the point A and C are stable and B is unstable, because here, as you see in the case of the point B, the radiation pressure force is exceeding the restoring. It is in the increasing direction at the point B. On the other hand, at point A and C, the restoring force is in the increasing direction. So therefore point A and C, that means when the movable mirror is at the location A or at the location C, then it will have a stable position. And in fact, this the whole effect, all these things have been experimentally observed, demonstrated way back in 1980s by a Harvard Water group for the first time. So now, because so far whatever we have discussed, we assume that the light react instantaneously to the position of the mechanical object. That means the force is always an instantaneous function of position, but it is not actually the reality. Now let us consider a cavity optomechanical system driven by a laser light. If the laser light satisfy the resonance condition of the cavity, then light will be able to enter into this cavity and there will be circulating light inside the cavity. And this movable mirror, say it displaces by let me denote the variable by x as usual. Now let us switch off the laser light. Then what happens? At first instant, the circulating light intensity is still the same as before. However, as time goes on, the light will leak away out of the cavity, and slowly the circulating power will decrease or diminish. So circulating power would diminish with time, because the photon is leaking away from the cavity. Okay, and the rate at which the energy inside the cavity decreases is called the cavity decay rate, and it is denoted by this symbol kappa, and this is called the cavity decay rate. Cavity decay rate kappa. Unless the mechanical motion is really slow, we have to take this cavity decay rate into account. Let us consider the radiation pressure force against position plot again to understand this little bit more clearly. So we have this usual plot, radiation pressure versus position, and we already know that where radiation pressure will vary like this. We'll just consider only one of the peak only. And by the way, the same kind of plot we are going to get for the circulating intensity inside the cavity as well. Now if we consider that the mirror is starting at some location, say at this location, say this is location, let me denote it by A, and this mirror here is moving very slowly, then as the position of the mirror is moved towards right, then you can see that the force will increase as we move towards, the mirror moves towards right. On the other hand, if it moves towards left, the force will decrease. This is easy to see. If the motion of the mirror is very slow, then there is no appreciable effect of the finite cavity decay rate. We need not have to bother about the cavity decay rate at this stage. Now let us consider the case where the motion is not that slow. That means this mirror is moving with some finite velocity. It's very small velocity. It's not the static case. This is the case for the dynamics. And in that case, this diagram would little bit modified, and what we are this is what I'm going to explain. What we are going to get is this. Let me just plot it. So we'll get a kind of this kind of a plot if the mirror is moving with some finite velocity. The movable mirror is moving with finite velocity. Let me explain what's going on here. As the mirror is moving towards right, the light intensity for some time still remains low. So suppose we are now here, okay, we are at this stage. This is the static case. So let me draw it a little bit with a different. Okay, so this is the dynamic case. Now the mirror is moving towards right with some finite velocity, and therefore the light intensity for some time still remains low compared to the static case, because the cavity still has to fill up the light corresponding to what would be expected for the new position. So we are slightly below the usual curve, that is the static one, of the force versus position. Then as we complete the cycle, that means if we go like this and go, suppose now we reach this position now, that means we are moving back to the left, the light intensity for some time here will remain higher compared to the usual static case. This red one, you see, red dot, the light intensity would be higher here because the light has to leak out of the cavity and it takes some time. Okay, so this is the reason we get such kind of an ellipse if we draw the force versus position plot. For such a situation, we must take the finite cavity decay rate into account. So this has actually important consequences. For example, the work done by the radiation pressure force on the mechanical object would be given by this expression. So that would be this closed integral. This is the radiation F dx, force into displacement. Now if we look at the plot carefully here, then we'll see that when we are here at the lower point, both the radiation pressure force and dx, displacement, has the same sign while moving towards right. Of course, in that case the contribution is lower than the usual one. On the other hand, force and dx, this force and dx would have opposite sign when the mirror moves towards left and has higher contribution than the usual one. So overall what is obtained is this. Overall this integration would be less than 0 because the negative contribution will be higher when we are at this location of the resonance curve. That means resonance peak is at this location, so we are at the left of the resonance peak. Then this integration, this work done would be less than 0. And what it physically mean is that the radiation pressure in such a cycle extract energy from the mechanical motion. So the radiation pressure force, radiation, or simply radiation force uh, extract, or rather let me say light, because the radiation pressure force is due to light. So I can say that light extracts energy from the mechanical motion, and if energy is extracted from the mechanical motion, so that will result in the so-called damping of the mechanical motion, and this is known as optomechanical damping. By the way, this kind of calculations were done by the Russian physicist Brzezinski and his co-workers way back in 1970. This kind of analysis were done, and this phenomenon is also called, as I said, it's called optomechanical damping. And such a mechanical object is, this kind of cantilever is usually coupled to fluctuating thermal environment, and because of this damping force, which is usually associated with little noise, it is also cools the mechanical mirror. So very simply, as we have seen, because the light is extracting energy from the mechanical mirror, so as a result the mechanical mirror is getting cooled down, and this phenomena is extremely important, and we will discuss it in great details later on also quantitatively, and this is called optomechanical cooling. And by this process we can actually, it's a kind of a laser cooling, in fact it is laser cooling. On the other hand, if we go to the other side here, and if we do the analysis here in this side, what turns out that this work done would turn out to be greater than 0. And what does it mean? It means that the radiation pressure force, work done due to the radiation pressure force, is greater than 0, means the light is going to dump energy into the mechanical oscillator or the mechanical mirror, and this will result in anti-damping or heating. It will result in anti-damping and heating. And if it hits, basically the more, because already as I said, this mechanical oscillator is coupled to thermal environment, and if further heating takes place, this thermal excitation will increase further, and also if this effect is pronounced, then it will also result in instability. Now we should be able to read out what's going on within the cavity in order to analyze the phenomenon associated with the static and dynamic cases which we have already discussed. This is easy because the cavity is simply an interferometer. So this is going to lead us to a discussion on what is called displacement readout. If the back mirror of this optomechanical system, so say this mirror is perfectly reflecting, then whatever the light is getting incident on this cantilever, because this is perfectly reflecting, it will completely reflected back, and the reflected light will suffer a phase shift. Now people or experimentalists look at this phase shift as a function of the position. A typical plot is plotted here, the phase shift versus position, as you can see from this diagram. So initially when you are away from the resonance, as you see here, there is no phase shift. There is no change in phase shift. Basically it is constant, because whatever light is getting incident, that is getting reflected back from the front mirror itself, because light would be able to enter into the cavity only if the resonance condition is satisfied. And when the resonance condition is satisfied, light enters and it get reflected from the back mirror, and then there would be phase change, and this is what is reflected in the slope here. So there is a phase change, and again as we move the mirror further, then resonance condition would not be satisfied, and the light would get reflected back from the front mirror itself, and the phase change will again remain the same, and there will be no phase shift actually. So phase shift would be given by uh, actually can be worked out, and if it is worked out, then it turns out that the phase shift is directly proportional to the displacement of the mirror and it inversely proportional to the cavity decay rate. So if the cavity decay rate is very small, cavity decay rate kappa has to be small. K small means theta large, so we'll be able to have a significant phase shift which would be easy to measure. And if kappa or the cavity decay rate small, that means the quality factor or the finesse of the cavity has to be large. And what does that mean? That means that the number of oscillations the photon will make inside the cavity will be large, or in other words, it means that the photon will survive inside the cavity for longer amount of time. And this is the reason why in cavity optomechanical system we need to have we require a high Q cavity or high finish cavity. So you see, from phase information, as you can see from this expression, from phase information we can have the information about the displacement of the mirror, and one can actually plot the displacement versus time curve for the mechanical oscillator. And a typical plot will look like this here. This I have taken from the review paper Cavity Optomechanics. Now you see the mirror is oscillating with a eigen. I'm just considering here only one eigen or normal modes of vibration is considered. One normal mode of vibration of mode of say oscillation of the mechanical oscillator is considered, and here this gamma refers to the damping rate of the mechanical oscillator. Damping rate of the mechanical oscillator. Somewhere we have taken gamma m like this, but it is the same thing. So initially, as you see from the plot, the amplitude rises here. As you see, amplitude rises because the thermal fluctuation from outside heats up the motion, and with time this fluctuation gets weakened, so it become weak, and the amplitude also depletes. Now the question is how large the variance of this fluctuation quantified by the variance of this harmonic oscillator or the mechanical oscillator. So you recall that variance is given by this expression. So delta x square is equal to x square average minus average of x square, but for harmonic oscillator we know already that the expectation value of x is 0, so therefore variance would be given by only this quantity. Now how we can estimate it? This is easy. We can do that by using the so-called equipartition theorem. So using equipartition theorem we can estimate the variance. Let me show you. It's very straightforward. So we know that the energy of the harmonic oscillator is half kx square or m omega square. Omega is the oscillation frequency of the oscillator, and then this is the variance, and this has to be equal to half kBt. Okay, because we are considering one mode of oscillation, so it implies that this variance is, or x square is equal to kBt by m omega square. So the amplitude of the fluctuation, so it implies that the amplitude of fluctuations varies like square root of temperature. Okay, this is easy to see. However, in fact, this is what is shown here, that it is, this amplitude is directly proportional to square root of temperature. So thereby we can extract information about the temperature just by measuring the amplitude of the fluctuation. However, it is important to note that the displacement time plot that we have shown here is far more complicated in reality, because here, as I said, we are considering only a single normal mode of oscillation, but in reality there is an infinity of normal modes in the mechanical structure, and the displacement of the mechanical oscillator at the position of the laser spot, you see, at the position of the laser spot here, the displacement consists of a superposition of all such normal modes of vibration, and all these different normal modes of vibration has different frequencies. So it is better to Fourier decompose it and look at the Fourier spectrum. The Fourier transform of the displacement x of the harmonic oscillator in a time interval from say 0 to t. So let us say the Fourier transformation of the displacement is denoted by x tilde omega, and it is Fourier transformation of the displacement x of t. So e to the power I omega t is the Fourier kernel. Then we are going to integrate in time, in the time interval say 0 to tau, and this is the normalization factor here, 1 by square root of tau. So this is the Fourier transformation of the displacement. Now this is obviously a complex quantity, and average of this quantity is 0, because we know that if we take the average of this x of t for harmonic oscillator, this is equal to 0. So better take the mod of this quantity and square it, and then plot x tilde. What I am saying is that you better take the mod of this particular quantity, x tilde of omega. Okay, let me write it properly. So you have x tilde omega, you take the mod and then you square it. Now let us plot x tilde omega mod square, this quantity versus frequency omega, and actually a typical plot is already shown here. As you can see from this plot, this is actually called noise spectrum. This plot is the so-called noise spectrum of the mechanical oscillator. Okay, as you can see, we are obtaining a pretty fluctuating spectrum here. However, in laboratory we will make a series of measurements, not just one measurement. So we need to take average of many such spectrums, and it means that it is better to plot, you better take this x tilde of omega mod square, and then you take the average and plot this averaged quantity versus the frequency. And when we plot it, this plot is called average noise spectrum of the mechanical oscillator. A typical plot is now shown here. So this is the averaged noise spectrum, average noise spectrum of the mechanical oscillator, of the mechanical oscillator. One thing you can quickly notice is that this spectrum is symmetric around omega is equal to 0, and what it here it means that x tilde of minus omega is equal to x tilde of omega. So this is what I mean by symmetry, and this is a typical characteristics of noise spectrum in the classical regime. Okay, now in fact it can be shown that this particular quantity x tilde of omega mod square, and if we take the average, and this is also denoted by this symbol as xx of omega, this is actually called noise spectrum. This is known as noise spectrum. This quantity is referred to as noise spectrum. It can be shown because we know the what is x tilde of omega, so it's very easy to show that this is equal to, or let me just write here that I can write x of omega, this noise spectrum is equal to 1 by tau 0 to tau dt1 dt2 e to the power I omega t1 minus t2, and we have x of t1 x of t2. It's very easy. If you find it difficult, don't worry, we'll actually address it in our problem solving session. Okay, this is what I have, and this particular quantity, you see, average of x at t1 and x at t2, this is known as correlator. This is called correlator. So let me write here, this is an important quantity, displacement at two different times. This is known as the correlator or the correlation function, and it basically gives us the information of the displacement of the oscillator at two different times. Now in the steady state, no point in time is special because it is steady state, and the correlator will depend only on the time difference. So it can be shown just by changing variables that I can express in the steady state sxx of omega, which is the noise spectrum, and this is x tilde omega mod square and the average. So it can be shown that it is minus infinity to plus infinity because all times are equivalent. So therefore this correlator, I can just change the time variable and I can write it like this. Okay, or this is also sometime it is symbolically represented by this xx of omega, and clearly either this quantity or this is the same quantity. This means that, or rather let us say this is simply, this quantity is simply the Fourier transform of the correlator or the correlation function. So what you see basically is that the noise spectrum is nothing but the Fourier transform of the correlation function, and this is known as, and it is referred to as Wiener-Khinchin theorem. So Wiener-Khinchin theorem states that the noise spectrum is nothing but it's simply the Fourier transform of the correlation function or the correlator. Now one can very easily calculate the area under the noise spectrum. So area under the noise spectrum, so what I mean by that is you just have to, by conventionally we'll put 2 omega, this will divide it by 2 pi, and this is the quantity we can calculate, and You know that this would be d of dt because we know what is this noise spectrum is. Then I have here, this is from minus infinity to plus infinity, d omega by 2 pi e to the power I omega t. Okay, and then I have x of t, x of 0, and this is very easy to calculate because you know this is nothing but the delta function. So this will lead us to, this will get it as x0 square here, and because all times are equivalent in steady state, so I can simply write it at x square. So what you see that the area under the spectrum give us the variance of x. So area under the spectrum gives us the variance of x, and we know that the variance of x is directly related to the temperature of the harmonic oscillator in thermal equilibrium. Okay, now let us find out the relationship between the noise spectrum. So relationship between the noise spectrum and the linear response of the system, linear response of the mechanical system. Now this linear response of the system is characterized by a quantity called susceptibility of the mechanical oscillator. So linear response is characterized, I will explain it, characterized by a quantity called mechanical susceptibility, and it is denoted by chi of omega at a particular frequency. Okay, and this relation between the noise spectrum and the linear response of the system, in statistical physics it is known as the fluctuation dissipation theorem. Or in short it is called FDT. Now we will actually not discuss it in details, only the theorem is needed for us, and that is what I am now going to state. The fluctuation dissipation theorem, or FDT in short, could be stated as follows. The noise spectrum Sx omega, or also it is denoted by this quantity, by this xx of omega, is related to the imaginary part of the susceptibility via the following relation. This relation is given in the classical limit. Okay, now let me explain it, and first let me explain about the susceptibility, because you already know what is this noise spectrum term. You are already maybe clear about it. So regarding susceptibility, you know that we have encountered this term called susceptibility in many places in physics and other areas of science. For example, if you recall the so-called polarization, say the polarization P that you encounter in electromagnetism, which is the electric dipole moment per unit volume in a dielectric, arises due to the application of an electric field, and this polarization P is directly proportional to the the external electric field that is applied, and it is actually expressed in this form. So P is equal to epsilon 0 chi of E, and here chi is the electric susceptibility, it is the proportionality constant, and this is what we call electric susceptibility. Okay, so what happens is that this polarization sometimes it's very strong at a particular frequency of the electric field, and hence it is also written in this form that this polarization is very strong at this particular frequency corresponding to the application of the electric field at that particular frequency, and this proportionality constant would be this way, chi of omega. Now chi, as I said, this is electric susceptibility, and this is actually called linear susceptibility, linear electric susceptibility. It is linear because you see the polarization is the linearly dependent on the electric field. However, there is, if the electric field strength is very large, then nonlinear terms are also has to be incorporated, but we will not go into those domain. Here we will assume that the electric field that is applied to the dielectric is not very strong. So in that case, the polarization and electric field, they share a linear relationship between them, and that is the bridge between this relation is actually given by the so-called linear susceptibility. Now in the similar way, the average displacement, say delta x, of the movable mirror in an optomechanical system is directly proportional to the radiation pressure force that is important on the mechanical mirror. Okay, so this is in optomechanics, we can have the similar thing. So obviously, hopefully you are now guessing it where this linear susceptibility term will come. Now again, here also the response of the mirror to this radiation pressure force is strong at a particular frequency, say omega, and this is represented in this form. So this displacement of the movable mirror, it's a very strong response is there at frequency omega, or I can simply write it as this displacement at frequency omega, and this is equal to the force, radiation pressure force at the frequency omega, and the proportionality constant here is given by this term, and this is your susceptibility term. Here this is called mechanical susceptibility because we are now dealing with mechanics. So this is mechanical susceptibility of the movable mirror or the optomechanical then mechanical system susceptibility. And by the way, here as you see there are two x I am putting. The first x is related to the response that we are looking, because we are looking at the response is this one, that is the displacement, and the second x here, this second x is related to the direction along which the force is applied. So here the second x, that means that the force is applied along the x direction, and the response is also measured in the x direction. That's what it means. So susceptibility is actually a complex quantity, and because it is a complex quantity, so let me write here that this mechanical susceptibility is a complex quantity, and that means that it has a real part and the imaginary part, and the imaginary part of this susceptibility is related to the dissipation of the system. So imaginary part of this mechanical susceptibility is related to the dissipation of the system. Let me explain this actually, dissipation of the system. To make you understand it, let me go back to the case of electric susceptibility, where we had this, say, polarization is directly proportional to the electric field. Now all of you must have done electromagnetic theory, and in electromagnetic theory you know that the so-called displacement vector, that is related to the polarization by this expression, epsilon 0 E plus the polarization, which actually is related to this. Epsilon 0 is the electric permittivity in free space, and epsilon is the electric permittivity in the medium. And from here, as we have P is equal to this, So immediately we can write, okay, let me write here. This means that I have epsilon E is equal to epsilon 0 E plus epsilon 0 chi into E. And what it means that I have epsilon is equal to epsilon 0 into 1 plus chi, that is the electric susceptibility. And this quantity epsilon by epsilon 0 is equal to 1 plus chi. Now if you recall that refractive index, okay, just I'm giving it a very, it's not exactly the way we should, but just to recall we should do, but just tentatively let us understand it this way, that speed of light is square root of epsilon 0 mu 0, and v is the velocity of, or the speed of light in the medium, that is again 1 by square root of epsilon and mu. If the medium is non-magnetic, then mu is equal to mu 0. So let us, we have that kind of a medium. So you have n is equal to epsilon by epsilon 0 square root. So therefore this quantity is simply equal to 1 plus chi is nothing but refractive index square. And this, if I can also, if say chi is a small quantity, then I can write n is equal to nearly equal to 1 plus half of chi. And refractive index is a complex quantity, so it has a real part and an imaginary part. Then I have this 1 plus half. Susceptibility has also a real part and an imaginary part. So let me write it let me write it this way, I into chi of I. So the refractive index, real part of the refractive index is equal to 1 plus half of chi of r, and the imaginary part of the refractive index is related to the imaginary part of the susceptibility, like this. Now you know that if a plane electromagnetic wave passes through a medium, its electric field at a distance, say z, is given by this E of z. You may be aware of Lambert-Beard law, so I'm going to that here. So say electric field initial is amplitude is E0, and as it passes through a distance z, so you have this phase vector here. And also you know that this k is the propagation vector, k is equal to omega by c into the refractive index. Okay, so therefore I can write, because refractive index is a complex quantity, so I can write it as E0 e to the power minus omega by c, the imaginary part of the refractive index. Then I have this propagation part of the electric field, that is I into omega by c, real part of the refractive index, minus omega t. So this part represents the propagating part and this represents the amplitude. Now what you see, okay, here z is also there, here also z is there. So what you see, that the amplitude is, as the electric field is propagating through the medium, amplitude is decreasing, and this dissipation of the amplitude is related to the imaginary part of the refractive index, and which in turn is related to the imaginary part of the susceptibility. Now you see that this imaginary part of the susceptibility is generally related to the dissipation. So hope you are getting now convinced. So in the similar vein, we can say that even in the mechanical case, the imaginary part of the susceptibility, mechanical susceptibility, is related to the dissipation of the mechanical system. Now if we go back to the fluctuation dissipation theorem here, as you see, this particular quantity, the susceptibility, is independent of temperature. It only depends on the spring constant, the damping rate, mass, etc. But you know that the fluctuation do depend on temperature, and hence in the fluctuation dissipation theorem, the temperature T is also appearing in the expression here. Now if we go into the quantum limit, which we will discuss in a tutorial problem, in the quantum limit, the FDT, the fluctuation dissipation theorem, is actually given by this expression, that is or this noise spectrum is equal to, it is equal to twice of h cross divided by 1 minus e to the power minus h cross omega by kbt, and this is related to, again, imaginary part of the mechanical susceptibility. At high temperature, the quantum version coincides with the classical version, and we'll discuss about it in the problem solving session. To appreciate fluctuation dissipation theorem, let us consider a classical damped harmonic oscillator. So you know the equation of motion for a classical damped harmonic oscillator is given by this expression. Here this small m is the mass of the harmonic oscillator. This capital omega, omega is the resonance frequency. So omega is the resonance frequency of the harmonic oscillator. This gamma is the damping coefficient. This is the damping coefficient. And this F is the external force. This is the external force. And F thermal, you know, even if there is no external force, in thermal equilibrium, we are and also you can get the hint from this presence of this damping term, that even if there is no external force, there is always some kind of a thermal environment, and this thermal environment is quantified by this term F thermal. Okay, now the idea in defining susceptibility is to look at the average response of the harmonic oscillator. And because this F thermal is a fluctuating term, so while we average it, then we will be able to get rid of the thermal force, and we on averaging we are now going to obtain this one. So if we average it, we will get mx double dot, this is the average, then m omega square average of x plus m gamma average of x dot, and F thermal average would go to 0, so we'll just left out with this external force only. And by the way, you let me just clarify that when I say x dot, I mean to say the time derivative of x. Okay, this is what I mean. Now it's always better to work in the frequency domain. So if we work in the frequency domain, by that I mean, say if we take x is equal to, say, x tilde e to the power I omega t, and f is equal to, say, f of omega e to the power I omega t, then if I take x dot, then I will get x tilde e to the power I omega t into I omega, and which is simply I omega x. So as you can see, I can always replace delta t or dt here. I can replace this dt by I omega. So that's the prescription when we go over to the frequency domain. So taking up this prescription, so d2 dt2 would become minus omega square, right? Taking this prescription, going over to the frequency domain. Okay, let me write here, going over to frequency domain, I can write it as minus m omega square plus m capital omega square minus I m omega gamma, and here I have this x. Let me just write average of this, but it is in now frequency domain, and this is equal to f of omega. Okay, from, because this displacement is very small, so I can simply, to emphasize that, I can write it as delta x of omega. So I have delta x of omega is equal to 1 by m capital omega square minus omega square. So here I have omega square minus I m omega gamma into f of omega. Okay, now you recall that this is the response of the harmonic oscillator and it is directly proportional to the force that is applied, external force, and this proportionality constant, as you know, this is given by the so-called susceptibility of the mechanical oscillator. So we can easily read out the expression for the susceptibility for this classical damped harmonic oscillator, and that is equal to 1 divided by m capital omega square minus omega square minus im omega gamma. This expression can be simplified, but before that, as you can see, this susceptibility is a complex quantity and it has a real part and the imaginary part, and imaginary part of the susceptibility is very straightforward to get and you can easily get it. And if you do the algebra, then the imaginary part of the susceptibility will turn out to be m omega small omega gamma divided by m capital omega square, then whole thing whole square here plus m omega gamma whole square. So this is what we have as the imaginary part. Now you see, imaginary part of the susceptibility is associated with the noise spectrum as per our fluctuation dissipation theorem. So this noise spectrum, which is actually the same as this term, and this is equal to twice kBt by omega and imaginary part of the susceptibility. So therefore the expression for the noise spectrum, this particular term, is equal to, if I put the terms from the susceptibility, I have twice kBt m gamma divided by m capital omega square minus omega square, this whole square plus m omega gamma whole square. Okay, this expression can be further simplified if, say, if gamma is small, dissipation is small enough, and you will have, say, gamma is far smaller than the frequency, say gamma is far smaller than frequency omega, then we can expand around omega is equal to capital omega. Then this expression for the noise spectrum, this expression can be further simplified and you can do it very easily, so I'm leaving it to you to do it. Otherwise we will do it in a problem solving session. So we'll have kBt divided by twice m omega square divided into gamma divided by omega minus capital omega whole square plus gamma by 2 whole square. So this is the expression we'll have. Now you see this expression has a Lorentzian form and the typical plot would look like this. So let me just plot it. So we'll have here the noise spectrum, let me put it here in the y-axis and omega in the x-axis. Then we'll have a plot like this. So we'll have a plot something like this. So you will see that this is symmetric around omega is equal to 0, and the full width at half maximum here you can easily find it out. Full width at half maximum would be gamma here. And what are the other things that we can find out? We'll find that the peak is situated at capital omega at the resonance frequency in both the cases here. Both the maybe I'm not drawing it properly, but you take it as a completely symmetric around omega is equal to 0. And what are the other things that we can find out from this simple diagram? Couple of things. One is, as you can see, you can find out the resonance frequency. The resonance frequency of the harmonic oscillator omega can be read out from this plot. And also what you can do, you can find out the damping rate. We can read out gamma, the damping rate, just by measuring the full width at half maximum of the spectrum. And also what we can find out, we can find out the temperature of the harmonic oscillator by working out the area. Find out the temperature of the harmonic oscillator by working out the area, and which is very straightforward because already I explained it, I think, earlier. So what I have to find out, I have to find out this integral d omega by 2 pi, and this is the noise spectrum, this area. You can work it out. It has to be twice, so twice because I have two peaks. Then I have 1 by 2 pi. I have 2 kBt by twice m omega square, okay, from this expression here. So okay, so I will have, say, minus infinity to plus infinity d omega gamma divided by omega minus capital omega square plus gamma by 2 whole square. Okay, if you do the calculations, and it's very straightforward, please do that, you will get twice kBt divided by m omega, sorry, this would be capital omega, this would be m omega square, and this is nothing but the variance. Okay, so that's how you'll be able to find out the temperature also, just by finding out the area. Let me stop here for today. In this lecture, we have completed our discussion on basic physics qualitatively, and also we discussed the so-called fluctuation dissipation theorem, which basically prepares us for discussion of cavity quantum optomechanics quantitatively from the next class onwards. And in the next class, we are going to discuss the classical regime of cavity quantum optomechanics. So see you in the next class. Thank you.